Hello there. In this video, we're going to talk about simplification. And so we're going to start with just a couple simplification of fractions. And when we're simplifying fractions, we have to remember to look for the greatest common divisor of the numerator and the denominator. So 10 and 16, well, and maybe you don't look for the greatest common divisor right away. Maybe you look for a common divisor. I know a common divisor is 2. 10 and 16, so 10 divided by 2 would be 5, and 16 divided by 2 is 8, and now 5 and 8 have a greatest common divisor of 1, so I know I can stop. So 2 did happen to be my greatest common divisor. Sometimes you do this and you find the answer right away, and sometimes it just takes repeated iterations. You have to be open-minded to the fact that sometimes it's going to take repetition, okay? So 54 divided by 90, this is an example. I'll just go ahead. I know that it has a common divisor of 9, so I'll start with 9, and I get 54 divided by 9 is 6, and 90 divided by 9 is 10. And then we can do, looks like another 2 for 6 and 10, so 6 divided by 2, and 10 divided by 2, this would be 3 over 5, and now 3 and 5 have a greatest common divisor of 1, and that's my final answer. Now, shameless plug, if you watched my greatest common divisor video, you know that 54 and 90 were one of the problems. So 9 and 2 being common divisors means that the greatest common divisor was 18. And so if I caught that right off the bat, I could have divided by 18. But this goes to show you that you can do it piecemeal if you so choose. Square root of 36, this is just a memorization of a perfect square. This is equal to 6. And a lot of times with computational square roots, we are tempted to want to say plus or minus 6 because negative 6 times negative 6 is also 36. But when we see square root of 36, we're just talking about the principal square root, and therefore we're just talking about 6. Square root of 100, same thing, just the principal square root of 100 is 10. And now here we get to the focus of the video, the square root of 80. What does this look like? Well, I know that the square root of 64 is 8, and I know that square root of 81 is 9. And this number happens to be sandwiched. 80 is between 64 and 81. It's closer to 81, so we're looking at approximately 8.9 something maybe, ... But we want to remember that if we have the square root of a non-perfect square, then that is going to be an irrational number. How can we simplify irrational numbers so that we can still expressly state it as exact? We have to remember that irrational means we can't write it as a fraction of integers, okay? We also can't identify a pattern, a repeated pattern within the decimal, and it doesn't terminate. So there is no way to write square root of 80 in its exact form in decimal form. So that's what the purpose of today's video is. So the first thing I'm going to do is I'm going to show you how I learned to simplify the square root of 80 when I was in high school myself, and then I teach you the method that I've kind of formulated over the years that I think works really well as a substitute. So the first thing we're going to need to do is we're going to need to list out some perfect squares. So I'll start with 1, 4, 9. This is why it comes in handy to memorize some perfect squares. 36, 49, pardon me, 49 and then 64. And I'll stop at 64 because the one after that is 81, and that's greater than this. And we want to be able to pick out some numbers from the perfect squares because we have to remember square root is the undoing of multiplying a number by itself. So which number can be simplified easily with the square root? Well, I see square root, I see 4. 4 comes out of 80. That would just be the square root of 4 times 20, which is nice. And then if I look at the 20 here, I can see another 4 can come out of that. So square root of 4 times 4 times 5. Now, that also means since we have the 4 and the 4, that 16 comes out of square root of 80. So maybe this is something you do piecemeal, the same way we simplified the fraction. Or maybe you recognize right off that, oh, 16 comes out of 80. So we could write this as square root of 16 times 5. It depends on how you want to do it, and I'll show you both ways from here on out. But you have to memorize perfect squares, and you have to know number structure to know what divisibility rules work to be able to do this. And as you can honestly tell, the larger the number, the more difficult it gets. Now, we have a rule in radicals that if we have the square root of a times b and a and b are greater than 0, doesn't say which one's greater, a or b, but just both if they're greater than 0, we can separate them into separate square roots. A times the square root of b. So for this first one, this would look like this. And I've got 3 numbers, but they're all positive, so I can do it. Square root of 4 times the square root of 4 times the square root of 5. And down here, I would just do square root of 16 times the square root of 5. And that's pulling it apart, because now what I can do is simplify wherever I see a square root of a perfect square. So let's go ahead and actually undo those circles. So square root of 4 is 2, and I've got that twice. But square root of 5 I don't have a simplification for. This is an irrational number, so I'm just going to have to leave it as square root of 5. And then I can do 2 times 2, which is 4 square root of 5. Now, if you didn't recognize 16 as a perfect square that comes out of 80, you can follow this path and get the answer 4 square root of 5. Now, if you did recognize 16, then we can do our simplification. Square root of 16 is 4 times the square root of 5, and you can see we get the same answer. So much like fractions, we can do it piecemeal, or we can do it all in one fell swoop if we recognize the greatest common factor, or in this case, the greatest perfect square that can be factored out of the number. So that's the old school way, identifying perfect squares and separating them with multiplication and simplifying the radicals that we can simplify. Here is the method I have devised over the years, and I like this a lot better, and I'll show you why when we're done with this problem. This is where our divisibility rules come in. So I'm going to create a factor tree for 80. Now, one of the divisibilities rules I see right off the bat is it ends in 0, so that means 10 comes out of it. And I got to think 10 times what gives me 80? That would be 8. Now, no matter how you create your factor tree, so long as you do the computations correctly, you will get the exact same factor tree. Maybe it looks different, but the same prime factors at the end. I know that 10 is 2 and 5, and I know that 8 is 4 and 2, and that 4 is 2 and 2. So this is the idea, is to break it down into its prime factors. And this is where the idea of a square root comes into play. We are undoing the process of squaring, or I should say multiplying a number by itself, which is squaring a number. So when I do this and I create my factor tree, I want to look for pairs, because that's a number times itself. So I look at my factor tree, I see a square root, I see a pair of 2's right there, and then I see another pair of 2's on the outer edges here. They don't need to be situated right next to each other in the factor tree, you just need to have the pair. Now note, this is like saying, this is 2 times 2, which is 4. And we know what the square root of 4 is. The square root of 4 is 2. This is all to say that when I see that pair of 2's, I can start to set up my answer. I see a pair of 2's, but it's coming out of the radical. So for every pair I get, I write a singular solitary 2. So that 2 might represent this 2, this pair that I was just looking at. And then for this pair right here, I've got an additional pair. So I will go ahead and put the 2 there. The final thing that we notice is that 5 is left by itself. It doesn't have a pair. That means it remains inside the radical. And we're using multiplication the entire time because we want to be able to put this back together. We pulled it apart with the factor tree using division, so we put it back together using multiplication. Now we can simplify. We've got the 2 times 2 is 4 square root of 5. All right, let's go ahead and look at another example, square root of 54. So we'll start with a factor tree of 54. I will go with, I see that it ends in 4, so I know it's divisible by 2. 2 times 27. And then from there, I get a 9 and a 3, and then the 9 breaks down into 3 and 3. So again, we're looking for pairs. I've got a pair of 3's right here. But then I've also got an extra 3 that's solitary. This 3 that I've just put the square around is not paired off, and neither is this 2. So when I set up my answer, I've got the pair of 3's that I can get 1 out of the radical. And then I've got to open up back the radical because I've got the 2 and the additional 3 that have to go back in there. And again, we use multiplication. And so I get 3 times 2 times 3 is 6. And that is my final answer. Now, this is less intuitive. It's a little bit more of a brute force way of doing it, whereas the more intuitive way is identify the perfect squares. You would get 54 becomes square root of 9 and square root of 6. And then you can simplify the square root of 9 to be 3 square root of 6. Ultimately, you have to be ownership over your own knowledge and decide what works best for you. So why do I like the factor tree method better? Let's go over it with a different example. Let's now look at the cube root of 54. Cube root doesn't affect how I start this problem. I'll create a factor tree, and it's the same number, so I'll just copy it down to 27, 9, 3, and then 3 and 3. But now I'm dealing with a cube root, which means I'm undoing the process of multiplying a number by itself 3 times. So in this case, I want to look for a group of 3. So I got those 3 3s right there, and now for every group of 3 I get one of those numbers outside the radical. And then, I'll write that bigger. And then I've got this 2 that goes back inside the radical, cube root of 2. And now there's less to simplify, but we still get our answer. This is why I like this method a lot better, is it can be mainstreamed to create an overall algorithm for cube roots, 4th roots, 5th roots. We would have to know that 54, if we're going to use the old school method, that 54 is cube root of 27, and that 27 is indeed a perfect square, times the cube root of 2, and then we can get our 3 out of the cube root of 27 times the cube root of 2. So you would have to memorize some perfect cubes. If it was fourths, you'd have to memorize some perfect fourths, and so forth and so on. This takes the guesswork out. If it was a perfect 4th we were looking for, we'd use a group of 4, and so on. Let's talk about one more example. Let's talk about a 4th root. Let's do the 4th root of 625. Now, 625, I happen to know to be a perfect square. So 625, its factor tree, I will break down into 25 and 25. Okay? And then 25s each get broken down into 5 and 5. And because we're talking about a 4th root, we are looking for groups of 4 from our factor tree, which I have a group of 4 5s right here. Now, also, I don't have any numbers remaining. I don't have any prime factors remaining, so my final answer is just 5. So 625, it actually happens to be a perfect 4th power. And this can happen when you do it. Say you didn't know what the square root of 81 is. And you just go, okay, let's make the factor tree. That's 9 and 9, and then 3 and 3, and 3 and 3. Well, we're looking for pairs, so I get a pair of 3s and a pair of 3s, but nothing left over for my prime factors, so 3 times 3 is 9. Now, if you did this, could you say, oh, I want to stop at 9 and 9, and just do the 9 and 9 and not break down the 3 and 3? You could do that. There are multiple varying ways you can do this. It all depends on the skills you build up as you go through it and what you can recognize on the way. Thanks for watching this video. Go ahead and give it a like and subscribe and leave a comment down in the section.